Yes, the audio works well. Okay. Yes, I think it works. Okay, so in the in these 2 days, we're going to discuss some quantum effects for black hole spacetimes, and we've seen a few different approaches to quantum gravity this week. But in this course, we will mostly focus on stuff that we can kind of reasonably assume to hold regardless of the precise quantum gravity theory. In fact, we will work on semi-classical effects more than fully quantum effects. And so let's start by discussing what is the plan of these 4 lectures. So in this first lecture, uh, I'm going just to talk about a few preliminaries. So stuff that we need to know. And for some of you, there might be something trivial, but I was also discussing with a couple of the organizers, and they agree that it's good to be all on the same page. If it is trivial for you, I hope I will still be able to say something that is going to be useful. Otherwise, I don't know, sleep for this hour and a half and see you in the next lecture. Then after the coffee break, we are going to discuss the Hawking radiation. So we are going to do the computation very similar in the way that Hawking did. So we are going to study the particle formation from black holes. So Hawking. Then I will so the you will see that I will try to limit all the technicalities at the bare minimum. I will try to avoid everything, every complication. Of course, the people among you that want to work on this stuff, then they will have to study those details. But I really would like to focus on what are the physical ingredients that are important, so that I think everyone working on quantum gravity should know. And if you strip out all the technical difficulties, whatever is remaining is the main cause of the effect. Then the first lecture tomorrow, we are going to define something that Zravan today actually already mentioned, which is the quantum stress energy tensor. So we're going to discuss these objects, which is something useful for when you are in some intermediate situation in which you are able to treat the gravity in a classical way, but you do have some effects due to the fact that matter is behaving in a quantum way. And there are a lot of subtleties in the issue defining these objects. We will not fully discuss them, but what we are going to do is to specify this for a Schwarzschild black hole. I will just give you the result that you will get, because I think that it can teach us a lot. And then I will also say a few things that can be done later on. And then in the last lecture, we are going to talk about the information problem. Um, as you can see, I have a much easier job than most of the other lecturers, because I was asked to talk about something which is very precise and not that huge. Of course, there will be, I mean, in principle, you could talk about this topic for a very, very long time, but at least giving the main concept, the main idea should be reasonably doable in 6 hours. And I'm not entirely sure how much this will take, but if there is time, let's say lecture 4B, in the last half an hour, 45 minutes, it would be very nice to talk about non-singular black holes. Um, so this is something which could get closer to something that I've done for research in the last few years. But I don't really expect to have time to cover this unless a sizable fraction of you really wants me to. So let me know by tomorrow, and I will cut a few things from here, a few things from here, and I will make sure to discuss some of that if many of you want. Okay. So this is the plan. Um, let's start with the first lectures. So the preliminaries that I was talking about, we can say two topics. The first one is going to be basics, really basics of quantum field theory and core spacetime. Quantum field and core spacetime is a topic that have a lot of subtleties, a lot of issues, but I'm really going to talk about something which is extremely, extremely basic. So for those of you that are already familiar, I'm going to define the Bogoliubov coefficient, which is what Sravan also mentioned today. But I will not enter into details of quantum field theory and core spacetime. And then we are going to talk about classical black holes. And what I mean by that, we're going to write down the Schwarzschild geometry that all of you know. And I'm going to discuss Penrose-Carter diagrams because we decided that given that I'm going to use them extensively in the next lectures, it's good. I'm sure that all of you are familiar with Penrose diagrams. But one thing is to know what they are. One other thing is to be able to look at them and immediately capture some information from them. So this is why it's good to also to talk about them. Okay. Any questions so far? Okay. So let's start from 50 in curved spacetime. And when I said that I was going to talk about, I want to reduce the technicalities to the minimum possible. One of the things I meant that we're going to consider a free scalar field. Free scalar field. You can do fermion fields, you can have potential, you can do whatever you want, but to understand the core of the issues, it's enough to consider a free scalar field. And so the field equation, box phi equals 0. So how do you usually treat this problem in flat spacetime? What you do in flat spacetime is that okay, you solve this wave equation, and you write the solution. You expand it some index I that is going to count the quantum number, is going to count the properties, and you expand it into modes that are positive and negative frequency modes. So AI, Fi plus AI, tag Fi star, right? Where this contains the positive frequency mode and this contains the negative frequency mode. And then, so what I mean by that is that if you do dt Fi, this gives you something like this, where this omega I are positive. And if you're confused by this you can just check that the simplest example is where Fi is so I is just the wave number, so the frequency, for instance, and so it's like f omega, and you just choose a plane wave base, right? So it's like proportional to e to the minus I omega plus I k dot x, where omega is equal to the modulus of k, right? This is a solution, and then this is what the standard base that you choose, right? But generically, this is the condition that you're chasing the positive frequency. And what do you do with that? So you do several things. You define a scalar product. You define the Fock space, the vacuum state, which is the states annihilated by all the operators AI, and then you do whatever you need to do. Now, what is the complication in Course spacetime? In Course spacetime, the complication is that it's not obvious how to define the positive frequency. Positive frequency for with respect to which observer, which time you need to use here to do this operation. And so generically, this is something that is not possible to define. Of course, in flat spacetime, you might have a similar problem because, of course, this is also in flat spacetime, in Minkowski spacetime. What is time, right? But if you're working in Minkowski spacetime, then you have a set of observers that are uh, the inertial observers, which are the observer with respect to whom you define the positive frequency, the positive and negative frequency. And you can perform a Lorentz transformation, but everything you do will be invariant to Lorentz transformation. So you have no issues. You do have so does not mean that all the construction, like the vacuum space, is unique, because also in flat spacetime you can define different observers, for instance, accelerated observers, which will have a different notion of vacuum. And this is, from those of you who know, is the Uru effect. The fact that an inertial observer and an accelerated observer, they do not see the same vacuum. But at least you can do something. You can define those privileged set of observers. How do we do it in Course spacetime? Generically, this is something that does not necessarily have an answer. But there is one case which is something which you can easily do that. And it is when your spacetime is either static or stationary. If your spacetime is either static or stationary, then there is no problem, because it means that there is a time-like Killing vector, and you can define the positive frequency modes with respect to this the time dictated by this Killing vector. So what I mean is that if there is a psi mu, psi mu, which is a time-like Killing vector, then you can do exactly the same expansion, and this relation will be replaced by something like xi mu, the mu fi equal to minus I omega I f, with again omega I greater than 0. So if you have a static spacetime, this is fine. You have a notion of time because the spacetime is a symmetry, and then it's completely fine. Stationary, the same. But most spacetime are not neither static nor stationary, so this does not work. But what is true in many physically interesting situations is that the spacetime is static or approximately static or stationary at early times. So you have something. So you start from something which is where you have a Killing vector, the time-like Killing vector in your region spacetime, psi in the in region, and then there is some interaction. So time goes up in the vertical direction, and in this region where you have the interaction, there is no notion of there is no preferred notion of positive frequency. So you don't really know how to do the splitting. And then at late times, the space-time relaxes again to some static or quasi-static or stationary space-time. So you have an out region. And so you can do the construction that you usually do in the in region and in the out region. Okay. Then something happened in the middle, we don't really know, but then at least there are something that we can discuss, which is very similar to what usually happen when you consider scattering of particles. You have free particles asymptotically before and after the scattering, and then you have this intermediate region where you cannot really define free particles, and uh, what you do is to compare the before and the after. So let's assume that we are in this configuration here. We can define the standard tools in the past and in the future, and let's see what happens. So uh, this means that we can do that construction there in two different ways. One will be in the in region, AI in, FI in plus AI in dagger, FI star in. And you can also do it in the out region. Out, out plus AI. This is out. Star out. Okay. No, these are just so the same state, but two different ways of writing it or decomposing it. And we can now do all the steps that I just briefly just said it before without writing anything. And this means that, and you will do that for both in and out region. So we can define, but you can always define a scalar products, for instance, phi 1, phi 2, which you can define as, let's see if I write it correctly. Phi 1 dt phi 2 star minus phi 2 star dt phi 1. Okay, the reason why you define the scalar product in this way is that you can check with this reduced field equation that this is constant, and this does not change for the evolution. And this is in plus space-time. In current space-time, it's exactly the same. You just need to choose some space-like hypersurface and do exactly that. Define it in this way. You have so you can choose the modes that are in a way that they are orthonormal. You just need to so basically you can show so F1 the in Fi in Fj in is equal delta Ij Fi in Fj out is equal 0, and then with the star. Sorry, this is always the same region. This is, you can show by consistency with this. This is minus delta Ij. And the same is going to be true for the out state. Fi out Fj. equal delta ij. And the other two, they are exactly the same. Yeah, it's the time. So it's uh, sorry, again, it's flat space-time. This is just the 3x at time. You do the splitting. In cool space-time, you just need to define an upper surface. And this time is the vector orthogonal to this upper surface. Yeah, but it was not very clear there. Thanks. It, exactly. So what you do that is, thank you very much. So what you do, um, what we will do, you will see, we will define it in one of the in and out region. This is what we're going to do. So we will define it particularly in the in region. Of course, I mean, in principle, you can do it wherever you want. It's just that you just need to choose a foliation. You just need to write this in a better way. This is yeah, I was just a bit sloppy. This is um, yeah. Anyway, yeah, we were going to do in the region. Yeah, sorry. Um, I don't want to enter now into details that we are not going to need. Yeah. Okay. Sorry. This is the flat spacetime, or you can do it also in the with the metric determinant. Mm, yeah, imagine this written here, but the generalization is trivial. Uh, now, yeah. So what else I wanted to say that we have the standard commutation relation of the operators A in and A in dagger. So beside that, AI Aj is equal to 0, AI dagger. And then you have AI Aj dagger equals to delta Aj. Now I'm using the notation h bar is equal to 1 to stick with the notation that was introduced before. And this is true both for the in and the out operators. Otherwise, you will have the h bar. The downside is that we will get a G term in the Schwarzschild metric, but you cannot have all. So we don't need to keep track of the h bar. Okay. And again, this is something that you do exactly the same way as you do in flat spacetime. You just need to do it. You just need to do it for both the set of modes. But now you have two sets of modes, and what you can do is to rewrite one set of modes in terms of the other ones. So given that this f in and f out, they both form a basis, you can always do that. So I can always just write down fi out. So these modes that I'm using in the out region as a sum of the f in and f in star with some coefficients that are the so-called Bogoliubov coefficients. F I in plus beta ij f. Sorry, this is j in star. This is something you can always do because these form a basis, right? And now we want to. So now the question is, how do we determine these coefficients, alpha I and j and beta alpha I and j? And we just need to use the fact that the scalar product was defined in a way that it was orthonormal. So we can let me just check that I use the same indices as in the notes, but also it could be that in the notes there are typos. So okay, maybe it's better just to do it. Yeah. So alpha ij, you can just do the scalar product with f out and f in. You will select alpha ij, right? So it's just f out e fj, and the same for beta. You need to do the scalar product with f I out and f in star. Et ij is equal to remind this minus sign minus f I out fj in star. Okay, and in, yes, thank you very much. And one more thing that you usually do in as I mentioned before, and that we really need to do, is to define the vacuum state, and then you can define the particle states and the multi-particle states. So we need to define again the vacuum states in the in region and the vacuum states in the out region. So let me write it here. Well, the vacuum states in the in region, I will denote it like this. And it's just the states that satisfy this property. And now I can define the out vacuum state. Okay.
The question is the commutation relation between A and A dagger here independent of what mode function we choose to expand phi?
Well, so we can, I mean, we need to choose the mode function so that this is satisfied. But this is all, I mean, it's always possible to choose everything which is normalized this way. And okay, so we have the definition of the two vacuum states. And you can, I mean, I'm sure you already know, so I don't need to write this down. You can write the states that contain, I mean, so the single particle state acting with a dagger. And you can do that both in the in and the out region, acting with the a dagger in on the states in, and a dagger out in the states out. And you can compute, you can construct your Fock space in this way. What we are really interested in doing is comparing these two vacuum states. And in particular, we want to know whether they are the same. So if we prepare the state vacuum in region, whether or not an observer in the out region will see it empty, or they will measure particles. So how do we do that? So to do that, we just need to compute the expectation value of the number particle operator, construct it with the operators in the out region on the in vacuum state. Okay, well, this n I out is just a dagger I, a I out. Okay. Yes, Ra. Hmm? What do you mean by exchange information? I mean, of course, there is going to be one-way causal communication, right? What I mean is that like the in region is the asymptotic past, or when the state is yeah. So this is going to be asymptotic past, and this is going to be the asymptotic future. So of course, there is information flowing from the past to the future. But if everything is causal, then it's going to be only one way. Yeah. Yeah. What do you mean? Like, mm, bring what? Bring yes. Yeah, this is exactly what I'm going to write down now. How to relate, because exactly what I want to do is to compute this expectation value, and I don't know how to act without at this stage. I don't know how to act without operators in the in state. So what I want to do is to write down a e out as a function of a as a function of the in state, right? This is yeah. Sorry. This is what I want to do. I want to write down. It was not clear. Just want to write down a out as a function of a in. And how do I do that? So as I said, this is the same field. I just choose a uh, different set of bases. So what I can compute, for instance, the scalar product phi with uh, f I out. Okay. If you compute this, we can compute it both with using this expression here and using this expression here. When I compute it with this one, I just select A, E out. A, E out. And then I need to compute with this expression here. And for that, I just use the definition of the Bogoliubov coefficient, which is telling me that the scalar products in and out are related to alpha ij and beta ij. Let me just write down the result because I don't want to make typos. So you get sum over j of alpha ij that come when you evaluate this term, alpha ij uh, a e in, and then when you evaluate this, you get minus ij, I think star, right? Yeah. A e out. Sorry, aj in. Okay, so we have this expression which is important. Thank you very much. And now with this expression, we can just evaluate this scalar product, right? Because this is just going to be in, and then we replace this, right? So we have the sum over j of alpha ej star, because we have this a dagger, aj in dagger minus beta ij aj in, and we have sum over k alpha I k a k in minus beta I j I k AK in dagger. And we just need to write this on the state, right? And then what are we going to get? So when you act with this term on the in state, you get 0. So the only non-trivial contribution is when you act with this term on here. And then again, when you act with this this one, you get the sandwich between the vacuum and a state which contain two particles, which is going to be 0 for orthogonality. And then when you act with so it's only the only important contribution comes when you act with this term and this term. And so what you get is yeah, let me write sum of j and k beta ij beta star ik and then you have a j in a k dagger in the state, right? And so when you act with both of these, you get a non-trivial contribution only when the indexes j and k are the same, because otherwise you will create a particle with the quantum number k's, and then you will try to annihilate this particle with j, which is not in the state. So this will just give you delta jk, and the in state is orthonormal. So this just gives you, with the Kronecker delta, this just gives you sum over j or beta ij modulus square. Okay, this is so to recap, this is the number of particles in the I with I label that we will see what I can be in the out state, evaluated in the in state, right? Square. Okay, so what is this equation telling us? It's telling us that the in vacuum state is not vacuum as seen from the observer in the out region. It's not vacuum when the beta coefficients are different from 0. When are the beta coefficients different from zeros? Look at this expression here. So when the beta coefficients are different from 0, it means that the splitting on the positive and frequency modes, remind that F contain the positive frequency mode and F star the negative frequency mode. It means that the splitting is different from the two observers. So the two observers do not share the same definition of positive and energy and negative modes. And this can happen when you cannot define a single time from in to the out region, right? So in particular, for static geometry, for stationary geometries that I was mentioning before, in which you can define the Killing vector, which is everywhere defined. Both the in and the out modes will have the same. So the in and the out observer will split the modes in the same way. And so in that case, for static spacetime, static or stationary, sorry. It means that this is 0. In particular, there is no particle production for stationary spacetime. You need a time dependence in the spacetime to create particles. And so here I'm going to ask you a question that we will go back to it in the next lecture. But I'd like you to think about it maybe during the coffee break. Is I still have the plan of the lecture. And the second lecture is going to be the Hawking radiation. Now, Hawking radiation, you probably know, is the fact that black holes are not black as in classical general relativity, but they do emit particles. But we know this partial spacetime, which is the one we will focus on, is a static geometry. Even if you allow rotation, you have a stationary geometry. But for static and stationary geometries, there cannot be any particle production. So what's going on? This is something that we will discuss in the next lecture. So how much time do you have for this lecture? 50 or 15? Okay. So is it clear, the question? I mean, I will repeat it. Um, there is a killing vector everywhere defined. Of course, I anticipate some answer. Well, maybe okay, no, maybe you will. I will not say one of the answer I expect, and so that yeah, we can discuss later. Well, this is a good moment to pose for questions, and if given that we have those unofficial breaks, if you want, yeah. We have time here and yeah, yeah. Yeah. So this is just because both f in and f out are a base of functions. So we use plane waves. You can always just change base. Uh, I think this will be very clear, and when we will do it a practical example, the next lecture. But this is just, I mean, these are just functions. So, for instance, I've written here like plane wave base, right? Uh, it's just that the splitting of the modes, positive and negative, is different. But also, yeah, it's not like you cannot have particle production. So, as I mentioned before, Unruh effect is something that different observer in flat spacetime, which is relatively a static spacetime, see a different vacuum, right? Because one observer is accelerating, and so the definition of the two vacua are different because one is accelerating with respect to the other. But there is a preferred notion of vacuum in flat spacetime, which is the one that's seen by uh, um, by inertial observers. I don't know why I couldn't remember the word inertial. By inertial observers, right? And the same is true here. There is going to be observers also in static spacetime that see something different, but it's because I don't know, we have accelerated observers also in flat spacetime and so on. But there is a way you can define your vacuum, which is universal for all the for all the manifold. Yeah? So there is a way, if you have a time-like killing vector, that you can define the vacuum state because you have that splitting over there. Which means if the space-time is static, there is a preferred time-like coordinate, which is the one in which the metric does not depend on time, right? Of course, even a static space-time can be written in a way that seems time dependent, right? But there is a preferred choice, which is the one in which the metric is apparent time independent. Yeah, exactly. Observer both in the past and in the future will agree on what is a vacuum. Right? Because this beta are zero. This is what yeah. So because this beta is relating it's telling you that the observer in the out region split the positive and negative frequency modes in a different way because this contains positive frequency as seen in region and this positive frequency in the out region. And if there is beta, it means that what is positive frequency in the out region is a combination of positive and negative frequency in the out region, in the in region. Okay, but if the splitting is the same, then the beta is 0. Okay. Mm-hmm. Yeah, this was the question. Yeah, that's the question. Yeah, this is the answer this is in the direction of the answer I was expecting, but it's not the answer that, well, but I don't want to say anything because we will we will talk about this after the coffee break. So this is the question, and if you want to think about it, we can. Yeah. Yeah. Forget that. Yeah. Yes. You will see an example in practice. I think it will be convincing. Mhm. Well, what you need to impose is that it's something which is conserved by the equation of motion of the state, right? So it's something it cannot be. So how do you define the time evolution in general relativity? You take foliation, right? You take something which is space-like region, and then you have some orthogonal vector from one region to the other, and you define this foliation, and you define the time evolution in this way, right? So you give sigma g, you need an initial condition on a space-like hypersurface, and you evolve it. What you want when you define the scalar product is that this is equal in each space-like hypersurfaces. It's not something that can change. Right? And I mean, we will see the specific example that everything is going to be clear. Mhm. No, you need to bring all the fields in the same foliation, which is what we will do tomorrow. Well, not tomorrow, after the break, the coffee break. No, stationary. You have time like killing vector. So Schwarzschild, for instance, or Kerr, or Minkowski. Yeah. Okay. I think we can say that unofficial break. Yeah. The box phi equals 0 in so I'm assuming that originally it's basically static or stationary, and also the end. That could be wave equation in core space time. It does not need to be flat. Okay. Sorry? Yes, yes. It has to be globally hyperbolic. Okay, so I think we can go to uh, the second part of this preliminary notion, which at the beginning I wanted to start with that, but given that I didn't know how much time I wanted, then this is what I definitely uh, needed to say in this first lecture. Now we're going to have some recap of Schwarzschild black holes, right? And this is something that whatever time I have remaining, I will talk about. So that's why I started with this, to make sure that I arrive to that point in time. Okay, so as I mentioned before, I'm going to use heavily the notion of Peros-Carter diagrams, because it's maybe because of my intuition works. I mean, it helps me a lot to grasp an intuition. So it's good to discuss what they are. I'm sure all of you are at least a little bit familiar with them, but basically it's just it's a way uh, to represent, to describe the property of a space-time within a finite region. And this works extremely well when we are in spherically symmetric space-time, because the way that you do that is you perform conformal transformation to arrive to the metric written in a system of coordinates that has finite span. And then we want to draw it on a whiteboard, which is a two-dimensional space. So what we do is to collapse the angular coordinates. So each point represents a two-sphere, and the coordinates are a finite span, so we can describe the full space-time within a finite region. So just to give an example that you should be familiar with. This is the Minkowski spacetime, and the important points of this diagram are, so first of all, it's important to check what are the boundaries. So the boundaries are, there is a point here called I minus, where all the time-like observers are originated. Then there is a point A plus, where all the time-like observer ends. And we have a point here, I naught, which is where the space-like observers is one end of the space-like observers. This vertical line is just r equals 0. And so space-like observer just go from I naught to r equals 0. And then we have these two null boundaries, which are chi minus and chi plus, which I'm very bad at writing, but right. And given that we have just performed the conformal transformation to go from Minkowski spacetime to something which is possible to draw in a finite region, it means that the causal structure is, I mean, this means that we can use it to describe the causal structure. So it means that radial, null radial is important. Null ray originate on Scri minus and go per like 45 degrees. Then arrive to r equals 0 and became a right going radial null way and end up on Scri plus. So this is what null observers. And time-like observers are observed that are always an angle less than 45 degrees. They start from I minus, end up on I naught. Yeah, you can have several time-like observers. And finally, you have space-like observers. Again, radial space-like observers that have, you cannot say where they start and when they end because it's space-like, there is no notion of time. But one end is I naught and the other end is 2 r0. Right? And so this is the space-time for the character Peros diagram for Minkowski space-time. We will use heavily the one for Schwarzschild that now we're going to discuss. But I think everyone is at least a little bit familiar with this, right? Someone doesn't know this you don't know this construction. So okay, so that's then it's very good that I have allocated time for this. Good. So this is so we are performing. We will see the kind of in detail this partial example. But what we do is we perform diffeomorphism. We perform coordinate transformation to arrive at a point in which we can rewrite the metric in a way which is a term which is a conformal term, which we will throw away, and then something which is in a finite region of space-time. Okay. So if you do that, it means that you can just draw the coordinates on a piece of paper on a whiteboard, right? And the fact that you're just throwing away the conformal term, it means that all the information about the causality are unchanged, right? Because you are not changing angles, you're not changing what is space-like into time-like, and so on. So if I want to know what are the time-like observer doing, I can look at a Peros diagram and see that they need to be less than 45 degrees because null observers are the ones that draw 45 degrees. So because time here it hovers up and the space is like that. So for instance, from here we can see that in Minkowski R equals 0 is time-like, which means that exists time-like observer that can just sit at R equals 0, right? And instead, null observers are the ones that move in 45 degrees. Right? And so this diagram is very, very well suited to discuss this kind of stuff, right? To discuss what is null, what is time-like, what is space-like. We can get a lot of intuition from here. What is really bad at doing is giving you intuition about space. Sorry, about distances. So the distances in a conformal diagram mean nothing because we are throwing away conformal terms. So this that you see here is Cray plus. This is all the infinity region reachable by null particles. This point here is the asymptotic future of every null observer. So, or every time-like observer. Right? And this point here is the future, the space-like future for so at infinite distance, space-like separated from us, all is collapsed into this single point. So you cannot use them to get an intuition on the distances, but they can be very good to understand causal structures. Okay, this is good. Otherwise, we can talk during the coffee break. Okay, and this is Minkowski. I promised that I was going to write the Schwarzschild metric with G different from 1 for the first time in my life, probably. Minus 2 G M over R T square plus 1 minus 2 G M over R d R square plus R square d omega square. This is R. My R and my omega sometimes are very, very similar. But this will. Okay. Okay, this is just the Schwarzschild, geometry in the Schwarzschild coordinates. And you know that there is a singularity at r equals 0 and a singularity at r equal to gm. The singularity at r equals 0 is a truly physical singularity. The singularity at r to gm is just a coordinate singularity, it's a bad choices of coordinates. And so this is some coordinates, but we are going to use heavily other type of coordinates. So we use coordinates that are well behaved at the horizon. So first of all, we introduce the null coordinates. I just don't think it's some coordinates u and v that are defined this way. V is just t plus r star, where r star is the tortoise coordinates, is r plus 2gm log r over. Let me just write and then discuss. Okay, so you can just say that you can just check that constant v is a null direction. So a null observer are observed with constant v. Just do a coordinate transformation. And then you can define again u e minus r star. Again, u equal constant is a null geodesic. And we can rewrite the matrix in several different ways. Here we are working the metric t and r coordinate. You can work with v r coordinate. You can work with the u r coordinate. You can work with the v u coordinate. Okay, but so the horizon the horizon coordinate singularities. It's at r star going to infinity. You can see because the log term diverges, minus infinity actually, which means v minus u minus infinity, right? So v and u are coordinates that are well behaved in some region of the horizons, but a combination of them always diverges at the horizon. And from just putting all of this together, you can also check how they diverge. And I might let me just write and then I could check. But I might do some mistake, but it should be look for sure the diverge exponential like p minus u over 4g m. It should be 1 minus 2m over r. Pretty sure this is correct, but let me check. Yeah, this is only true near the horizon, right? You can just expand this term here and this relation here. And so, given this type of divergency, you can see you can get an intuition of how to define proper horizon penetrating coordinates, which are the so-called Kruskal coordinate. You just need to reabsorb this divergence here. Right? So instead of this going to minus infinity, you want something that simply goes to 0 at the horizon. And so to do that, you just introduce the Kruskal coordinate. X v over 4gm and u equal I put a minus here, but v over 4gm. The minus is just so that the derivative with respect to of capital U with respect to small u is positive, so they both grow in the same direction. And so if you do this and check here, it means that this relation here at the horizon, v minus u goes to minus infinity. It just means that capital V times capital U are 0 at the horizon, right? So we get something which is well behaved at the horizon. And then you can see that the range at which your coordinates are changing are u goes to minus infinity to 0, and v goes from 0 to plus infinity, right? Because this is how we are defining them. But you can just simply extend them, just making a copy of them in this one in the positive region and this one in the negative region, right? So you can actually go to something which is defined minus infinity plus infinity. You can do the analytical extension. And this is necessary to do this extension because otherwise your space-time will be geodesically incomplete, because you will find geodesic that arrive to v equal u capital U equals 0 infinite amount of proper time, and then you will have space-time which is geodesically incomplete. But you can just extend, and you can define these coordinates that are perfectly well behaved everywhere. And then, so we've written, I didn't write down the metric. I mean, this is very fast, but I'm sure that you should be at least a little bit familiar with all the coordinates and so on. Because all what I wanted to, well, we will see more in more detail now, but so the point is that the horizon v times u goes to 0, right? So instead of having coordinates that diverge at the horizon, they are just 0, and then we can extend beyond the horizon simply like this. And then finally, if you want, you can define some u tilde, which is just a compactified version of u and v. So arctan of u and v tilde arctan of v. Why so? Because then u tilde and v tilde will have a finite span, Right? So if you do all these steps just with time, you see all the how the metric transform. You will get something that is in a finite range of coordinates. And in front of it, you will have this conformal factor. We just throw away this conformal factor, and we can draw the Peros-Carter diagram of Schwarzschild spacetime. Right? This was very fast. I just sketched it, but probably you're familiar. And if you're not, I mean, what we are going to use are just some of the results. So uh, we don't really need. I mean, I try to justify a little bit this construction, but if you just do that, and you will get the correct result. So we can, if you do all these steps, we can draw the Peros diagram, which is something that we are going to use in next lectures. And okay, out of time. And it looks like this. So well, I just draw it first, and then we can discuss it. Okay, so let's see how are all these, what are all these uh, segments that I draw. So just by raise of hand, who of you have already seen this Pyros diagram? Most people, I guess, have already seen that. Yeah, I was expecting it. Okay, well, uh, but even if you've already seen it, it's good to, because we are going to use it heavily to look all of the important points. So here in this Minkowski spacetime, I had one point where all the null, the all time like observers were originated. Now we have 2 points, I minus, let's call it left and right, and then we have a space like singularity in the past, which is the Schwarzschild singularity that are equal 0. When you do this extension you do the analytic extension of UMV, you create beside the singularity of Schwarzschild. In the future, you create a copy in the past, and then you have everything. You have double, right? You have I naught left, right. Why did I switch to left and right? Right. I plus right plus left. I naught left, and then you have scribe plus right, scribe minus left, scribe minus left plus left, right. Okay, and let's see how all these coordinates that we need, how do they behave, right? I wrote here these 4 coordinates, and also there is the Kruskal one, right? U and V. At different moments we are going to use all of them. We are not going to use this compactified version. It was just to needed to draw the diagram. So the so T and R coordinates are coordinates that are respectively time-like and space-like outside the horizon. This is the black hole horizon. So here E equals constant radius, do something like this, right? Whereas R equals constant, do something like this. And here you see you have a copy of your space-time. And then let's call this H plus and this H minus. We also have a copy here. So what are the coordinates that are well defined everywhere? So on scribe minus, we have coordinates where so v goes from minus infinity to plus infinity here, right? So v, this coordinate v that we were discussing, the past timeline coordinate, is the coordinate that grows on square minus from here to here, right? And because this is some coordinate, this is in the past, so t goes to minus infinity. This is, but r also goes to plus infinity, so the sum can be finite, right? And so here we have v minus infinity to plus infinity in here. Whereas both small u and capital U are minus infinity. So they're divergent here, right? And the same goes, the opposite goes here. So here we have coordinates. So u is a good coordinate on the square plus, and v is a good coordinate on square minus, right? What about the horizon, especially this h plus horizon? So the horizon, we know r is equal to m, right? Okay. The horizon we have r equal to m, and we have the coordinate the coordinate singularity if we express in terms of t and r. Yeah. G is not one. This is the first time I forgot G. Okay. Second. Yes, there. Okay, it's too far. Okay, so R is equal to GM. So what about small v? So v equal constant. As I said, v equal constant before is a null geodesic. Null geodesic goes 45 degrees, and v is defined as t plus r star, right? So t grows, r star decreases, which means that in this diagram it's left going coordinate, right? So v equal constant is something like this. Okay, this line is a v equal constant, which also means that it's perfectly well defined at this side of the horizon, this h plus. So v is okay on h plus, at least the right one, right? What about u? So u is also at a null coordinate. So u equal constant is something, given that it's t minus r star, is something like this. And so it goes from something which is minus infinity here on square plus, square minus, to something which is plus infinity on the horizon. So u goes to plus infinity on h plus, right? Okay, so u b coordinates, the second, no, the fourth line, the small u and small v coordinates, they are not good coordinates to describe the horizon because they can describe this region one, but the u diverges here, right? On the other hand, on this side and the minus in the past, this other branch of the horizon, it's the opposite. It's the other way around, right? We still have r is equal to 2gm, 2gm. This time I remember g. Yeah, no, this is what I mean here, or like on h plus, on h minus. So what I mean is that the coordinates are in this at the horizon is equal to 2gm. Well, it is. It's just what I mean is r. So r equal constant are these lines here, right? So in particular, at the horizon, it's equal to 2gm. What do you mean it's not the same coordinate? It's not a star. Yeah. Yes. Yeah. 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 Oh yes. Okay. Well, what I mean is, yeah, when you restrict on the horizon, this is well, okay, we can call it RS, but what I was uh, well, I mean, I'm just saying, like, also V, right? I'm saying that it's well defined and U goes to plus infinity at the horizon, right? So what I mean is the coordinate R at the horizon is RS and it is equal to 2gm. Definitely true. I agree. And the same is true here, like U is a coordinate that goes from minus infinity here to plus infinity here, right? And um, on the horizon it goes to plus infinity. And so small u and small v, they are not a good coordinate to describe everywhere. But what about no, sorry, I was discussing h minus here, and as you were saying before, u equal constant are these type of lines. So u is perfectly fine on h minus, but v is divergent on h minus, is minus infinity, right? Because v goes to minus infinity here to plus infinity here. What are the crucial coordinates? So u is okay on h minus, but v goes to minus infinity on h minus. Okay. What about capital V? Capital V, it grows in this direction like V. So it's well defined coordinate to describe points on h plus. So it's okay on h plus, and it's equal to 0 on h minus r. So we have a good coordinate to describe this, and the same for capital U. Equal to 0 on h minus r is something okay. It grows from minus infinity to plus infinity on h. Okay, so this is. I hope it was clear, but this is just to show the different terms, different coordinates. What is their value? This is something that's going to be important in the third direction. Yes, Rama? I'm never going to go to Euclidean time. So this is so. I mean, of course, you can do that, but in this lecture, I'm never going to go to Euclidean time. This is the space time for an eternal Schwarzschild black hole, and this one is for Minkowski space time. Now, black holes are not really eternal. They are created by gravitational collapse. And we are also going to need the space time, the diagram for a black hole which is created by gravitational collapse. And what I mean created by gravitational collapse is I want something which in the past looks like very similar, very good approximation Minkowski. Because the matter is very sparse, and then the collapse grows. So in the past, I want something that is resemble this region here, and then in the future, I want something that resemble this region here. right? And so I can draw the diagram for a collapsing black hole just by gluing uh, these two space-time. And this is how it looks like. This is the collapsing matter. So the metric is something that we don't know in here, or uh, it depends on the specific model for the matter. And then you have something which is Schwarzschild outside of the matter. And so why these are both useful? This is simple to deal with because it's a static spacetime. This is described as an actual astrophysical black hole. And this approximates very well this one at late times. And with statement, what I mean is that the late time region in this diagram approximates very well the late time region of this diagram. Okay. So we will use both of them. And again, here, this is as okay, you don't have this other region, this other asymptotic region, this copy of the universe in this space-time. But again, you have I minus, you have I naught, you have I plus. Let me delete this circle. You have scribe minus, you have scribe plus. And again, as before, we can define coordinates that are good in this space-time. And in particular, you can see that now the v coordinate is everywhere well defined because the v coordinate was well defined on this horizon here, and this one is no longer part of the manifold. So you have a good v coordinate here, which goes from minus infinity to plus infinity. It basically keeps the time on square minus. It counts the time on square minus, this v coordinate. And then we had again the u coordinates on square plus, which is it diverges at the horizon, goes to plus infinity. Right? So we can describe this space-time. Some coordinates are well defined for this space-time are, for instance, V and R. These are everywhere well defined, contrary to the static geometry. Or you can define in terms of the Kruskal coordinates. That's also fine. They're defined everywhere. So in particular also here. But their range is not going to be from minus infinity to plus infinity. They're going to have a smaller range. Any question? It was a bit, maybe a bit confusing. I need to apologize, but I hope that the message is clear. This is just, we are looking for coordinates, and you should remember how different coordinates, where they're well behaved and where they diverge, and especially in the third lecture is going to be useful, but of course I will remind this result. So if there are no questions, I have another couple of things. They could be useful. And we can discuss about the different notions of horizons. I just used the word horizon so far. I never say the word event horizon, which is what sometimes people do, because I'm very picky on saying when something is an event horizon and when it's a different type of horizon. And given that I still have a few minutes, I can make this distinction because I think it's relevant. So the definition of the event horizon that you're probably familiar with is the boundary of the space-time region that does not escape to infinity. That is not possible to escape to infinity. And this means, for instance, in this diagram, what is the region that cannot escape to infinity is all this red region, right? So the event horizon is the boundary of this region. So it's this line here. This is the event horizon. If you are outside, you can end up either in the singularity or on square plus or on I plus, right? But if you're inside, you are doomed to end up in the singularity. So this is a useful definition in many cases, but this is it's important to know this is a global definition. So in order to know if a point is is inside an event horizon or not, I need to have information about the full history of the universe, the full manifold, right? Because if I draw only a section of the space-time and I don't continue it, and I ask you, is this point inside the event horizon? There is no measurement you can perform to answer this question because you have no idea whether or not asymptotically with a outgoing null direction, whether I will end up in the singularity or if I will end up on Sky Plus. Right? There is absolutely no measure you can make. So in most contexts, the notion of event horizon is physical, meaning that if you perform an observation of a black hole, you are not looking at an event horizon. There is absolutely no way you can say that there's an event horizon. What you can measure is the quasi-local definition of an horizon, which is the trapping horizon. So a trapping horizon is a quasi-local definition which capture the same concept and is the boundary of this. I'm not going to write down the specific mathematical definition because it's not useful. It will take not long, but it's fine. It's just the boundary of the space-time region that uh, that is locally bounded, which means that observer in this space-time region cannot escape locally, so can only move in the direction of decreasing radius. And I can give you an example in this diagram here. In this region, we are inside the space-time, the event horizon, because if you continue the null ray, you will end up in the singularity. But I don't know the geometry inside the matter. I don't know if I'm seeing something which is a trapped region or not. The simple example, if you have a null shell collapsing, the interior geometry is just Minkowski. So if you are here inside the null shell, you cannot measure any gravity. You are in flat space-time. So that's why the trapping horizon is a definition which is different. Is something you can actually measure. Um, and so yeah, so uh, maybe well, I don't have time to write down the specific. Okay, so it's just something that is locally is trapped, which means if you are in a very strong gravitational field, you cannot move in the direction of increasing radius, right? So your radius, your area radius that you can measure decreases with time. You cannot move in the opposite direction, right? If the space-time is static, this happens also inside the event horizon always. It is a one-to-one, it's exactly the same, right? But if it is dynamic, the fact that you are inside the event horizon does not imply that. So if you have a null shell which is collapsing, the metric inside the null shell is going to be Minkowski, flat space. Outside the null shell is Schwarzschild, right? So if you're here, you are in Minkowski spacetime. You are in flat spacetime, but you are inside the event horizon. So there is no measure you can perform to understand that you are inside the event horizon, right? And this is because you are not inside a trapping horizon. So you're not in a trapped region. So if you look at R equal constant radius, they do something like this, and you can easily go towards higher radius, right? And the opposite might also be true. You can have uh, you can have something which let me draw in this way. If I draw constant R radius, something like this. Um, Just a second. Yeah, no. Something like this, very weird, but so basically they are space-like. This means that if you're here, you can always go in the direction of decreasing radius. Right? But you are not inside that event horizon. That this is possible if you violate the energy condition and so on. But this is just to say that these concepts are not necessarily the same. And in some cases, it's going to be important to distinguish between one or the other. Right? Um, how much time do you still have? Okay, then let's have a break. Okay. Even okay, so the question is: any freely falling observer can fall into the singularity in a finite proper time. So even after Kruskal extension, the manifold is yes, absolutely true. The even yes, so even after a Kruskal extension, the manifold is still geodesically incomplete. So the answer is absolutely true. Yes. So the Kruskal extension is curing the coordinate singularities, but not the truly physical singularity that are equal to 0. That I'm not touching.